So now let us describe this picture in a semiconductor much more clearly. So we say that we have a we have a valence band which is mostly filled states, and we have a conduction band which is mostly empty states. And what do you mean by states? You have these potential solutions to Schrodinger's equation that in a valence band is definitely taken up by electrons, whereas you have potential solutions to Schrodinger's equations that are not yet taken up by electrons in the case in the conduction band. Now upon receiving some energy, so these are electrons that are held in the outermost shell of your atoms. So upon receiving some energy, so for example say thermal energy, the electron can get excited and can jump across this forbidden gap and into the conduction band states and occupy a solution to Schrodinger's equation that defines it to have an energy level in the conduction band. Now this electron is free to move about in the crystal, and it is something called as a free electron. It is of great interest to us to count the number of free electrons in the crystal, because that is it provides a measure of the current through the crystal. Now the electron that has left the valence band and moved into the conduction band leaves behind a vacancy which is called a hole. Okay. And the hole is basically a state that has now become empty. Okay. So there was a state which is occupied by an electron. The electron left that state and moved into the conduction band, and therefore that state has now become empty and it is called a hole. So therefore there are plenty of holes in the conduction band, okay, or plenty of vacancies in the conduction band, but we are not interested in those. We are only interested in the vacancies in the valence band, because once again it is these vacancies that can lead to that can add on to charge transport, and we will see how in a minute. Now it is possible for the electron, since these energy levels are all very fine, very small, it is possible for the electrons in the valence band to jump into these vacancies and therefore create a new vacancy. So let us say that these electrons were to jump into these vacancies, and therefore this vacancy which is located here would appear to move through the states in the valence band because of electrons occupying it. Okay, so it is possible for the hole to appear like as though it is moving in the valence band because of these electrons from other states coming in to occupy it, thereby leaving the previous state vacant. Now in the case of crystalline silicon, which will be in some sense our role model of study, let us say 3-dimensional crystalline silicon, which is basically a periodic arrangement of silicon atoms in 3 dimensions, we find that at room temperature at 300 Kelvin we do have about 1e10 electrons per cc, that is per centimeter cube, being promoted from the valence band and into the conduction band states. Okay. So this is when the silicon atom is pure and it is kept in the dark with no light, no voltages or no currents through it. So it's at something called as a thermal equilibrium condition. It is possible for electrons to move in, and therefore it leaves behind holes which have the same concentration. Now here we also define these 3 energies. The bottom of the conduction band, okay, so this is all the conduction band states. The bottom of the conduction band is given this very special symbol that we will use throughout the course, and it is called as EC. The top of the valence band is something called as EV, and this gap, which is the forbidden gap, which is EC minus EV, is given a symbol EG. So let us continue discussing this picture here. So we saw that it is possible for the electron to take up energy and jump into the conduction band. Now we are going to have several definitions. Now the first definition is to do with something called as an intrinsic semiconductor. An intrinsic semiconductor is essentially a pure semiconductor. That is, it does not have any impurities such as dopants present in it. The second definition has got to do with something called as a thermal equilibrium condition, which means that you have prepared the semiconductor and we keep the semiconductor in the dark, that is, it is not exposed to any photons. And we also do not apply any electrical bias, say for example voltages or currents across the semiconductor. The semiconductor is kept as is in the dark, and the only source of energy for the electrons could be the thermal energy due to the ambient temperature. And this thermal energy is given by kT, where k is the Boltzmann's coefficient. So please do not confuse this term now with the wave vector. It's the Boltzmann's coefficient, and T is the temperature. So that's the order of the energy given to the electron due to the ambient temperature. Now, a material in thermal equilibrium is in no way silent. Okay, it is not a very quiet material. There are many processes happening in a material in thermal equilibrium. So for example, an electron in the valence band could acquire the thermal energy and could jump into the conduction band, and you will find many such electrons doing it. But statistically speaking, on an average, nothing changes, which means that if there are n electrons that jump into the conduction band, you have n electrons that are coming back into the valence band. Okay. So this process of creation is very finely balanced by the process of destruction. Destruction implies the loss of free carriers. Okay, which is a more appropriate term is recombination, which we will look at later in the course. And also you could have electrons moving about in the crystal. Say an electron in the conduction band, a few electrons could be moving about in one direction, but this movement basically which basically constitutes a current is completely balanced by an equal number of electrons moving about in the opposite direction. So there's a lot of randomness and a lot of events happening at thermal equilibrium, but statistically speaking these are all averaged out in time, and you find that there are zero currents and zero shift from the so called equilibrium position at thermal equilibrium. And this complete balance is something called as a detailed balance. Now if you were to take an intrinsic semiconductor, an intrinsic material, which means a pure material, and keep it at thermal equilibrium, which means that you do not throw light on it, etc., etc. And the only source of energy for that is the ambient temperature. Okay, so we give it some temperature T and therefore some thermal energy T, and we take an intrinsic material and keep it at equilibrium. Then we would find that there is a certain number of electrons that acquired this thermal energy and jumped into the conduction band states. And this concentration of electrons in the conduction band states, which is basically the number of electrons above EC per unit volume of the material. So this is the electron concentration in the conduction band states, is given a symbol N. And the number of holes in the valence band per unit volume, that is the number of holes below EV per unit volume, or the number of vacancies, is given a symbol P. Now in an intrinsic material at thermal equilibrium, there is a certain value for N, and for an intrinsic material that value is given a special symbol, and it is called as the intrinsic carrier concentration, which is a technical term which we will use quite often, and is given a special symbol Ni. So yes, in a material in general you have N number of electrons per unit volume in the conduction band, P number of electrons per unit, P number of holes per unit volume in the valence band. But for this special condition where you choose an intrinsic material, that is without impurities, and you keep it in thermal equilibrium, then N would be equal to the special value which is Ni. And in that case, what would the value of P be equal to? It would also be Ni. And why is that? It's because in such a case it is only the electrons that jumped from the valence band to the conduction band that contributed to Ni, and these electrons would have left behind an equal number of holes in the valence band. Therefore, in this condition your N and P would be at thermal equilibrium, you will find that N is equal to P is equal to Ni. Now, in silicon Ni is about 1E10 per Cc at 300 Kelvin, but Ni is clearly temperature dependent, it is very strongly temperature dependent, and we will see this dependency much more clearly later on. And Ni is temperature dependent. Why? It is temperature dependent because if I increase the temperature, more electrons could take up the ambient energy, the thermal energy, and get into the conduction band. So, just before we conclude this discussion, one more finer aspect. So, in the case of silicon, for example, the energy gap is of the order of 1.12 electron volt. Okay, so that is the energy gap in 3-dimensional crystalline silicon. Now, at 300 Kelvin, what is the order of the thermal energy provided to provided to the electron? The order is of the order of K, it is of the order of kT, where K is the Boltzmann's coefficient, which is of the order of 10 power minus 23 joule per Kelvin, and T is the ambient temperature, which is about 300 Kelvin. And therefore, this product has got a value of about 10 power minus 21 joules, which is of the order of 10 power minus 21 divided by 1e minus 19, which is 0.01 electron volt. So, does it imply that since the electron has got 0.01 electron volt as thermal energy, does it imply that that no electrons can climb across the gap and into the conduction band at 300 Kelvin? The answer is no, that is not the case. Okay. Now, this value of energy, which is kT, is an average value, and there is a large distribution. If you were to look at the number of electrons versus the energy that they possess because of thermal energy, this distribution has got a very large tail, and the average energy possessed is about of the order of kT. But you do have enough electrons having an energy that is larger than your 1.12 electron volts, and it is these electrons that can actually jump across and into the conduction band. And the number of such electrons per unit volume in the case of intrinsic silicon at 300 Kelvin is your 1.05 into 10 power 10 per Cc per unit volume, that is particularly per centimeter cube, and at 300 Kelvin. So, let us now start to look at the impact of applying an voltage, an external voltage on the electrons in a crystalline semiconductor. So, let us say we have a semiconductor crystal and we now attach a battery across the semiconductor crystal. We apply a voltage VA across the semiconductor crystal. So, let us say that is the positive terminal of the battery, that is the negative terminal, and therefore, this establishes a low electric field inside the semiconductor crystal. So, we will denote the electric field by this symbol, and we will say that the electric field is it is a weak electric field inside the semiconductor crystal. So, now in the semiconductor we have already seen that we have the conduction band states and we have the valence band states, and at some temperature, given some temperature T. So, let us say the T is greater than 0 Kelvin, and let us say for some practical purposes T is close to say 300 Kelvin, and we see that the electrons would take in some thermal energy, and some of these electrons will be able to jump from the valence band states into the conduction band states, and in the conduction band these electrons are free to move about in the crystal. So, you therefore have free electrons in your semiconductor crystal, and these electrons are free to move about. So, the moment these electrons, which have basically got a negative charge, so they have got a charge of minus 1.6 into 10 power minus 19 coulombs. So the moment these electrons see this electric field, they will respond to the electric field and they will start heading towards the positive terminal of the battery. So all the electrons will start moving towards the positive terminal of the battery. And this movement of the electrons is something called as drift. So drift is a very particular term used when the electron moves because of an applied electric field. Okay, it is a very characteristic charge transport mechanism which is the response of electrons to an applied electric field, and we will look at this idea in much more greater detail later on in the course. Now the movement of the electron in the semiconductor lattice is quite different from the way it would move in, say, vacuum. So if an electron were to be placed in vacuum, and if an external electric field or if a voltage were to be applied across these plates in vacuum, we would see that the electron would experience a force and therefore it would begin to accelerate. And we could write Newton's laws of motion to say that the mass and the acceleration of the electron is equal to the force that the electron feels. Now this mass which we would take for an electron in vacuum is something called as the rest mass of the electron, or the mass which is of about 9.1 into 10 power minus 31 kilograms. But in a semiconductor crystal, the movement of the electron is a lot more complex. So firstly, imagine the electron sitting in a lattice. Okay, so these are all the lattice atoms. So you have all the silicon atoms in the semiconductor lattice, and these silicon atoms have got a positively charged nuclei, and it's got an electron cloud which is negatively charged. And now we have this one free electron that is migrating through this lattice. So let us say that is our free electron that is responding to the applied electric field. Now this free electron has got a negative charge. So since this free electron has a negative charge, it will tend to polarize all the nearby atoms of silicon. So all the nearby silicon lattice atoms will now get polarized in such a manner that the positively charged nucleus is drawn towards the electron and the negatively charged cloud of electrons is pushed away. So we will see all the silicon atoms surrounding in the vicinity of the free electron getting polarized. So now the movement of the electron is quite unique, right? So you have these positively charged nuclei closer to it, and therefore this polarization effectively creates a kind of a trap for these electrons. So if you want to imagine the movement of an electron in a semiconductor crystal in a more poetic fashion, let us say you are asked to run on a very hard surface. Okay, so you have a person running on a very hard surface. So on a very hard surface, with each step of the foot, there is a good normal reaction, and then the person could actually run very quickly. But now let us say a person is asked to run on a very slushy ground. So you have a slushy ground wherein the soil or the surface is very soft. So with each step of the foot, the soil would actually sink inside, and then you will have to pull the foot out and then take another step and the soil will sink in again. So it would appear to be much more difficult for the person to run on this very slushy ground, because each time a person puts his foot down, his foot is stuck in a small gravitational potential well. Okay, or you could also imagine a person running on a rubber sheet, wherein with each step the rubber sheet is distorted, and it's not a very friendly surface to run on, although it could be a lot of fun. So the movement of the electron in the crystalline semiconductor could be imagined to be exactly that, right? So with this polarization, the electron sinks into a little well which is created by these positively charged nuclei, and then it continues to move about, and then it polarizes another bunch of atoms and so on and so forth. And this entity which constitutes these polarized atoms and this electron is something called as a polaron. And this is something that we will never use in this course, but it's just a definition that I am giving you since we are discussing this. So that's not the only complexity with regards to the movement of the electron in a crystalline lattice. So if there is an electric field, the electron almost never goes through the semiconductor without interacting with the lattice ions in a much more stronger manner. So the electron, so all these lattice atoms are also vibrating about because of thermal energy. So you can imagine the silicon atoms to be a bunch of hard spheres connected by springs, and there is a certain spring constant depending on the kind of bonding, etc. So these atoms are all jiggling around because of the thermal energy that is available, and this movement of the lattice the lattice points, or this movement of the silicon atoms results in a very strong interaction with the free electron and results in the free electron getting scattered. So the electron, the way it would move in response to an electric field in a semiconductor is, if you have an electric field in this direction, the electron would move, it would scatter off from this atom, it would move away in another direction, it would scatter through another atom, it would probably encounter a defect somewhere, which could be an impurity or a dopant ion, it could be a charge defect, for example, and that would result in some other kind of scattering, and so on and so forth. So so the electron tries to accelerate due to the application of the field. It does in this little minuscule length scale. The electron does accelerate. So you could say that the electron is trying to accelerate in that little length scale, but then it very quickly scatters and exchanges momentum and comes to a rest, and then it accelerates once more and then scatters again, and so on and so forth. Therefore, the effective movement of the electron in the crystal would appear to have this periodic bunch of velocity jumps. So you will see the velocity increase, and then there will be a scattering, and then there will be a velocity increase and scattering, and so on and so forth. And therefore, unlike in vacuum, the electron does not completely accelerate throughout. It instead exhibits a constant velocity, okay, and this is something called as the drift velocity of the electron. And it's a technical term, and it is a term that describes the velocity of an electron in response to an applied electric field, which we have already defined as the drift transport mechanism. So if we want to continue modeling the electron using Newton's laws of physics, some very simple relations, we need to consider all these complications with regard to the microscopic phenomena, which is the microscopic aspects of the electron's interaction with the lattice. So that's the movement of the electron with respect to the applied electric field. But now let's look at the hole, or the vacancy here. So you also have vacancies in the valence band. So you have the electrons in the conduction band that are moving through the lattice in this particular manner. But then you also have these pots, or these empty states left behind by the electrons that got promoted to the conduction band, and these vacancies were called as holes. And essentially these are solutions to Schrodinger's equations, or these are energy levels that an other electron could come in and occupy. So let us say that you have these states all being filled with electrons. Now these electrons too would like to move in response to the electric field, okay, but they do not have enough energy to jump across into the conduction band and then move through the crystal. but instead they could jump from one location in the valence band to another, and because the energy required there is quite small, and therefore in some sense respond to the applied electric field. So let us say that this electron were to jump into this vacancy, which implies that it would leave behind a vacancy, it would occupy the state and leave behind a vacancy here. And further, let us say this electron now jumps into this vacancy, which implies that it would occupy this state and create a vacancy there. And if this process were to continue, you will find that the electrons all in the valence band also try to respond to the field and try to move towards one side, and it would appear like as though the vacancies were moving towards the other side in the opposite direction. Okay. So therefore, in response to an applied electric field, it is not only the electrons in the conduction band that respond to this field, but it would also appear that the holes in the valence band are responding to this applied field, and they are moving in the opposite direction as compared to the electrons in the conduction band. So that's the picture, that's the effective picture the holes would represent, because as the electrons move here, it would appear like as though the holes or these vacant states are moving in the opposite direction. Therefore, we can in fact treat the hole as a particle, as a charged particle that can contribute to charge transport, because it does participate in charge transport, but we can assign to it a positive charge of 1.6 into 10 power minus 19 coulombs. Therefore, we can say that the electrons, okay, so just to summarize this discussion, we can say that the electrons in the conduction band have a charge of minus 1.6 into 10 power minus 19 coulombs and contribute to current. But the holes in the valence band have a charge of plus 1.6 into 10 power minus 19 coulombs and also contribute to current. Therefore, in a crystal, in a semiconductor crystal, if say this is the semiconductor crystal, we would have in response to an applied voltage, say let us say we have applied a voltage VA, so that is the positive side and this is the minus negative side. It would appear like as though there are two kinds of particles in the semiconductor. You have the free electrons, so these are the electrons in the conduction band, and then you also have the holes, which are the holes in the valence band. And these electrons will have a negative charge and these holes will have a positive charge. Therefore, in response to the electric field, since the electric field direction is in this as shown here, the electrons will all run towards the positive side and the holes will all run towards the negative side of the battery. Okay, so this is the effective response of the electrons and holes to an applied electric field. So therefore, we could treat the holes as particles of positive charge that are running in the opposite direction to the electron, and therefore these two currents would add up. You will have, if you look at the effective current, since you have negative charge due to the electrons moving in this manner, you have a current due to electrons moving from the positive side of the battery to the negative side of the battery. And since you have the positively charged holes running in this manner, you will have a current due to the holes also moving from the positive side of the battery to the negative side of the battery, and therefore the hole current and electron current would add up to constitute the total current in response to the applied electric field. Therefore, we need to have a combination of empty states and carriers in order for charge transport. So just to give you some analogies here, okay. So let us play around with this. So if you were as kids, you might have played with this little game, okay, which would appear like that. You would have seen a lot of tiles, and these tiles would have had say a certain picture, say a picture on them that you needed to complete by arranging these tiles, by moving these tiles around and arranging them in proper order or in a proper sequence. And you might have always seen that there was one empty slot in this puzzle, and therefore we could move these tiles around and therefore complete the picture. Now if I were to ask you as to what would happen, as to how quickly would the tiles move if there were no empty slots. So let us say all the slots had a picture in them, okay, and if you were asked to solve this puzzle by moving these tiles around, the answer is probably that you cannot solve the puzzle because the tiles cannot move around. And why can't they move around? Because there are no empty states or empty places for the tiles to move about. Two tiles cannot occupy the same spot. That's exactly the case with electrons. Now on the other hand, if I were to have no tiles at all and give you only empty spaces and asked you to asked you to move the tiles around or tell me or measure the flux of the tiles in this game, the answer is 0, because you have only empty states or empty spots and there are no tiles for you to move around. Okay, so that is equivalent to having only empty states and no free carriers. So again the answer is 0. But on the other hand, if I were to give you a few tiles and if I gave you a lot more empty slots, okay, instead of 1 I gave you, let us say 3 empty slots, now it would be much easier and you would probably solve the puzzle a lot quicker because you can now very quickly move a lot of these tiles around. Okay, so it is a combination of empty states, okay, and free carriers that leads to current.